Okay, so number 4, modeling data using exponential functions. So we've got exponential growth function whose y values increase as the x value gets larger, but not at a constant rate. Okay, so constant rate would be linear, right? If we were adding 2 each time or something, that would be linear. And we've got exponential decay functions, so like we saw with the half-life question from yesterday. Part A, Sonia did an experiment to determine the cooling curve of water. She placed the same volume of hot water in 3 identical cups. Then she recorded the temperature of the water in each cup as it cooled over time. Her data for these 3 trials is listed in the table below. So let's put this into our calculator. And you may want to clear the calculator, so second plus 7 for reset, left arrow to get to all, hit enter, and then hit enter on 2 for resetting all. I think I can either have the calculator or so I'm going to then go to Stat, Edit, and in L1 we are going to put the values. So in L1, this goes in L1, this goes in L2. So you're going to go 0, 5, 10, 20, 30, 40, 0, 5, 10, 20, 30, 40, 0, 5, 10, 20, 30, 40. So 0, 5, 10, 20, 30, 40. So that'll be for trial 1, 0, 5, 10, 20, 30, 40. Trial 2, 0, 5, 10, 20, 30, 40. Trial 3. Then we move over to L2, and we're going to enter the numbers that are sitting in our package, which I'm going to have to grab a package. Exponential function. Okay, we've got 80. $8, 61, 61, 45, 34, 96. I just kind of make sure things line up so that I'm putting in my next one at 0, so I'm at 0 here. Okay, so that's 75, 66, 59, 44, 32, 23, and again we're at 0, 78, 68, 61, 44, 33, 25. Okay, so it says enter the data in your calculator. So we have all of this data, time in L1 and temperature in L2. Plot the data. Okay, so what we're going to do then is we're going to look at the scatter plot, right? It's going to look at the points. So to do that, we need to set a window. And so our x values, which is time, go from 0 to 40. But, we may want to extrapolate, which means to go beyond the time of 40. Maybe we want to go to 50. And I'm going to put the x window at -10, just so that we can see the stuff that's at 0, right? If we put that at 0, it's going to kind of cut through the edge. So I'm going to go from -10 to 50, and we'll go by tens. And our temperatures, well, it's kind of boiling water stuff. Let's go from 0 to 100, also by tens. All right, so we put the x values, in this case the time, in L1. We put the y values, in this case, the temperature and L2. We did 3 trials, so we've got 0, 5, 10, 20, 30, 40, so on, twice. We've set a window. We've taken our x min a little below 0, just so we don't kind of cut the edge off at 0. We'll be able to see the points that way. To look at the points, we need to turn on the stat plot. So you can do that by going second function and y equals, and that takes you to the stat plot. And then you can turn on the plot, hit enter on the on, and then hit graph. Okay, and it's not a new cost. So here's our scatter plot, right? This is just showing the points. And you know that by going to -10 here, we can see these 3 points at 0. If we just went 0 to 50, then these would just kind of be, we'd just be looking at the edge of them, right? Just like a cutoff part. You can see that we've got, it's going to put a square for each point, and we've got kind of a, blurry thing. This is the 3 values. There's 3 values in each one. These are all pretty close to the same. So that's at what, 10, 20. So if we look at 20, we're probably going to see values that are pretty close to the same. But I had to give up my values. So there's no values left. Wait, I've got them here. There we go. So at 20, we had 45, 44, and 44, right? So those 3 values are almost all the same. And that's why it looks like there's just one square here, but it's really showing all the squares. All right, what's next? So we entered the data, we plotted it. Okay, that's a scatter plot. Use your calculator to find the exponential regression function. So we're always going to tell you what type of regression to run. So how do we run an exponential regression? So like every regression, starts off with stat, go over to calc, okay, we're going to calculate something. So if we're doing linear, it's number 4, quadratic is number 5, cubic is number 6. And then, so we are looking for exponential. So you can just keep arrowing down. I'll show you a faster way on the next one. Okay, and it's 0. And then hit enter. So you're now going to see one of 2 screens. Either your screen looks just like this one, or you just see the word EXPREG, right? And does anybody have that one? Does it have a bracket, or is it just EXPREG? Just EXPREG. Okay, on this screen, it's showing the X list and the Y list. On the other calculator that doesn't show these, it's defaulting to those. Okay, you don't see them, but they're there. Frequency list we don't want, so we go now to store regression equation. Okay, or just leave it where it is. And now we're going to put in y1. So to get y1, we press the vars key, we go over to y vars, y variables. We hit enter on function, and we hit enter on y1. So I'll usually just say vars, y vars, enter, enter, right? So hit the vars key, move over to the y variables, hit enter twice. So we want this to say store regression equation 1. On the other calculators, you just wanted to say EXPREG and then y1, which is saying exactly the same thing, right? It's got the exact same values as we have here. So if you just hit enter, it's going to calculate, and for us, we're going to go to calculate and then hit enter. And it's going to say, I'm running the exponential regression, and it gives us the values. Does it say rounding? What does it say to round to?
Nearest 100.
Nearest 100th? Okay, so 78.68. Graph, round values to the nearest 100th. Okay, so y is equal to 78.68, 0.97, I think, to the power of x. Okay, let's just verify that. Yeah, so rounding to the 100th, 700th, there's 2 decimal places, 78.68, 0.97. To the power of x. You've got to write it that way. Do not just write down y is equal to a times b to the x, and then say a is equal to this, b is equal to that. You'll get no marks for it. Okay? I won't give you any on the diploma. You won't get any. So you need to write it as a proper equation. Use the graph of this function to find the temperature of the water after 15 minutes. Okay, so now we hit graph. So there's our scatter plot. And because we told it, run an exponential regression equation, or run an exponential regression, and we told it, put the equation into y1. So when we hit graph, it plots the points, and then it plots y1. So the line is the equation, right? It's the exponent, and it's a pretty darn good fit. We look at that and we say, yeah, going through all the boxes. Pretty much if there's three kind of stacked, it's in the middle of them. It's kind of on the bottom corner of these guys. It's going pretty close to the middle of that, and that. It's a good fit. In the old days, we used to, there's a thing on the calculator that will tell you how well an regression fits. Okay, we don't do that now. We just tell you run this regression, right? Run an exponential regression. And it said find out, where do I want to get the sheet in front of me, and find the temperature of the water after 15 minutes. So our x values, our L1 is time. So we want to put in a time of 15. So we go second function, calc, which takes us to the calculate menu. And number one is value. And value is you saying, okay, I'm going to give you an x value. So you hit enter. And it says, what's the x? So I'm going to give you an x value of 15, 1, 5. And I want you to give me the y value. So I'm going to hit enter, and it's going to give the corresponding y value, right, which is 51.006. So call that 51 degrees. Okay, use graph to find temperature, 51 degrees. Make sure you have degrees on here, right? There are units. Now you could write degrees Celsius, but the temperature up here is in Celsius, so yeah, that's cool, 51 degrees. Use the equation from B to calculate the temperature after 15 minutes. So this equation would be y is equal to 78.68, 0.97 to the 15. So we go to our calculator. The second function quit just takes us out of the thing, and we write 78.68 and 0.97 to the 15. 78.68 bracket 0.97 bracket to the power of 15. Okay, and we recognize that's an exponential function, right? It's in the form a b times b to the x, right? So a is 78.68, b is 0.97. Hit enter, we get 49.82. Temperature after 15 minutes, 49.8. How does that compare to the value from C? Close, but not identical. Close. Close. Not identical.
Is that just because of rounding?
Basically, that is exactly because of rounding. So the calculator is using the y1. If you look at y1, if you go to your calculator and you look in y1, go to y equals. See 78.681240740285 times 0.9715. That's going to keep going. I'm using about 12 decimal places, right? But we used, to do this, we used a rounded value. Just rounded to the nearest 100. Okay, so it's close, not identical, due to rounding. Okay, the answer in part C is more accurate. Answer in C, this guy, is more accurate. So basically, it's better to run the stuff off of your calculator than to use the equation, right? Just due to rounding. Okay. It'll just be closer. Use the graph of the regression function to find the time at which the water. Okay, hang on. So when we did 15 minutes, should be here. What do we call that? We're putting in 15. Interpolation or extrapolation? Which one? Inter, right? Because it's in between, right? We're in between. We're going with data that's in between values. When you interpolate on a graph, that's usually pretty accurate, right? Because you know the data on either side of it is accurate. You've actually measured these. So that means the number you get should be pretty accurate, right? And what did we get? It was like 51 degrees, so 61, 45. We know it doesn't cool. It's not cool. It's not a straight line, right? So we don't just say, well, what's the difference between them and split that in half because that's halfway. That doesn't work. That's linear. Would work that way. If you're going halfway here, you'd be going halfway here. This is exponential. Okay, so it fits. It's on the curve, which we saw. Use the graph of the regression, find the time at which the water is 50 degrees Celsius. Okay, so the other type of thing we do with the regression is, so one is, you give me an x value, I'll give you the y value. So we just did that, right? Second calc, 15, put in 15 minutes, it gave the y value, which is temperature. If we give it the temperature, that has to go in the y. Temperature is a y value. So we need to graph 50 as the y value, hit graph, and then find the time, and we do that using second calc intersect. So we're interested in the intersection point between these two lines, and we know the y value is 50, right, because that is 50. What we're interested in is what is the x value, which will say at what time. Okay, so when you run an intersect, what I do is I just move to the point of intersection. So move your cursor, your little blinky thing here, move it to the point of intersection, because it's asking for the first curve, which you notice is nice on the color calculator, right? The first curve is the blue curve, and I hit enter. Then it asks for the second curve, which is the red curve, right? And if your calculator is black and white, you'll see y2. It'll go y1 and then y2, and hit enter. And then it wants a guess. So it says, put me about where they intersect. So I just like to shortcut that. Just move to the intersection and hit enter 3 times, right? One more enter. And we get the time. So 15.689, call it 15.7. The time at which the temperature, so 15.7 minutes. Now, we can look at some other stuff about this, right? This is about, what was it, hot water? Yeah, cooling curve of water. So we heated the water up. So what does this mean? What's this number? What's the 78.68? Sorry? Yeah, the A value, right? Which in this case is what? What does the A value mean here? Starting temperature, right? So this is the starting temperature. Okay. Now you can see the starting temperature for that was 80. This one started at 75. This one started at 78. It's saying putting all three trials numbers together, we have a starting temperature of 78.68 degrees Celsius, right? What does this tell us? 0.97. So is it growth or decay? How come? Yeah, so B is between 0 and 1. 0.97 is between 0 and 1. So this is exponential decay. Exponential decay. Okay, and that goes back to like day 1, right, or day 2, when we first started looking at the A and B value of the function. Right, we're saying, oh, well, you can tell the A value is going to be your starting value. The B value, if it's greater than 1, is exponential growth. This thing would be growing. And if it's between 0 and 1, it's exponential decay. So we know all of that looking at this. What's the starting temperature? 78.68 degrees Celsius. And what's going on is exponential decay. We actually can tell a bit more about this, but we'll look at that more tomorrow based on the B value. Oops. Center the data in each table. Determine which set represents exponential growth and which represents exponential decay. So let's just look at this table. So is this growth or decay? growth. How do you know? Yeah, so the y values are increasing, right? And they're not increasing linear. So linear just means if I went from 1 to 3, if I went up 2, this is going up 4. But here I go up 2, this goes up 8. And here I go up 2, but this goes up like 16. And here I go up 2, but this is going up 38. So you're going up by a different amount. That's generally an exponential. Okay, so find all of these. So basically, we're going to run another exponential regression. So to start with, easiest thing is go to y equals and just clear out what's in there, right? So we're just going to clear. Go second plus, go into the memory menu, and we want number 4, clear all lists. So number 4 is clear all lists, and then hit enter, it'll say done. So that's just going to clear out everything that we put in there from the temperature thing, right? Because we want to start over, we want to put new data. Okay, how do we do that? We go stat, edit. It's going to be in L2, just move back over to L1. Put in the numbers. So we got our x values are 1, 3, 5, 7, 9, which seems a little odd. And then our y values, so we arrow over and we put in the corresponding y values. So 2.03. And whenever you're entering data into the calculator, make sure that you check it over before you do anything. Because if you make a mistake entering it, then you're going to get wrong answers, right? And if it's multiple choice, maybe the mistake you make is one they made. I mean, you're lucky in multiple choice if you don't get one of the answers, right? Because then you know you did something wrong. Say, oh, I didn't get one of the answers. I did something wrong here. Let me try again. You go back and look at it. If you do get one of the answers, well, I mean, 3 out of the 4 answers that are there are the wrong answer. So you may have just made the mistake that they anticipated you would make, right? But in numerical response, there's no feedback, right? I mean, you get, unless you get a number like 75,000 and you know that it has to be 4 digits, or you get a number like -10 and you know that numerical response must be a positive number. There's nowhere to put a negative sign. Don't try and fill a negative into the box. Oh, this is negative, right? You can't do it. They must be positive. It's asking us for end behavior and stuff, so maybe we want to draw the graph of this. So it goes from 1 to 9. This goes from 2 to 68. So I'm going to go like 0 to 10, and I'm going to go 0 to 100 on that one. So go to the window, say 0 to 10 by 1s, and 0 to 100 by 10s. Okay. It doesn't hurt to expand the window a little bit, just give it some room. You may want to see what this thing looks like. We know it's growth, so after the 63, if we kept going beyond 9, we know that it's going to get larger values. You can look at the scatter plot, right? If you just go graph. So because the stat plot is still on, okay, we didn't turn it off. We cleared the list, but we didn't turn off the stat plot. Now, if you clear the list and then you don't put anything back in it, and you're trying to graph something in y equals, your calculator is going to say error, invalid dimension, or invalid dim. And what that means is your stat plot is on, but you've got nothing in the table. You've got nothing in L1, L2, so it's got nothing to plot. Okay, so if you remember that, then just go turn the stat plot off. Go second function y equals, get into the plot, and turn it off. If you can't remember that, just clear your calculator, re-enter your data, start over again. Okay, so if you're getting an error on your calculator and you're not sure how to fix it or how to get rid of that message, clear your calculator, start over. Okay, that's what this looks like. We go to stat, over to calc. We're going to run an exponential regression, which we now know is 0. So let's assume we don't remember it's 0, but we know it's not on here. Fastest way is to up arrow, and it'll take you down to the bottom, and then you can get up to 0 a little bit faster, right? Instead of 10 down arrows, right? So if you know that regression is off the screen, then just hit an up arrow and you'll get there faster. So then I hit enter on that. If you remember exponential regression is 0, you can just hit a 0. It'll just pop up with exponential regression. Okay, do whatever you got to do for your calculator. So on this one, we're going to move down to store regression equation. And for the people without that, you're just going to put the y1. Okay, so it's vars over to y vars. Enter, enter. And basically what we're just saying is when you run the regression, put the equation into y1 so that not only will I get the scatter plot, but it'll also show the actual exponential function. Hit enter, go to calculate, hit enter. Runs the regression. So it's so rounding the nearest hundredth, 1.50 for A and 1.54. So y is equal to 1.50 for A, 1.54 for B. Okay, so round nearest hundredth, necessary. And we can go look at the graph. So now I'm going to hit graph. So if it really is exponential data, then it should fit the graph. The graph should fit very nicely through the points, and it does. Okay, so that's good. And let's answer some questions. So what is the y-intercept? You know that. You knew this day one, day two, whatever. 1.50. Right? The y-intercept is A. A is 1.50. What is the end behavior? What's it doing? Q2 to Q1 increasing.
The y-intercept always great.
Yep. And A is always the y-intercept. Q2 to Q1 increasing, right? Which tells us that we're dealing with exponential growth, right? Which we knew looking at the table of values, we said this is exponential growth. Okay, which means when we run the regression, then we expect to see a b value that's greater than 1, which we do. Okay, so things match up. What is the domain of every exponential function? Yeah, so set of all x such that x belongs to the reals. Now, if we were just talking about this, and we were going nowhere outside of this, then we might say the domain is, well, it could just be the numbers, 1, 3, 5, 7, 9. Okay, and then you don't have to say real numbers. So if that data was discrete, where you could only have one of these things, or 3 of these things, or 5, or 7, or 9, right? It always had to be an odd number of them. The domain might look like that. It might look like this. Okay, we don't really have a lot of context to it, right? So you need more context. And a lot of your diploma exam is there's a big setup, right? You see the box on the test that you get. You see this box says use the following information to answer the next question. That's setting up the context for you. Okay, this thing we're running this. Let's say that's what do we got? 1, 2, 3, 4, 5. Some kind of a 5-sided die where you can roll a 1, a 3, a 5, a 7, or a 9. Then that's our only values. That's all you can get, right? Maybe it's any number between 1 and 9. Then we would say the domain was that. What's the range of a general exponential function? What's the range of every exponential function? Yeah, so y must be greater than 0, right? We can never get 0. Okay, because there's an exponent, there's an x. You're taking some base to a power of x, you can never get 0 out of that.
You don't get the graphic thing.
If it's shown somewhere else on the test so that you could have done that, so on the diploma, I'd say probably you have a good shot at losing a mark. Okay, because generally somewhere on that diploma exam, there will be a domain listed. So if we kind of list it's like, you know what, no, look, we listed domains for you elsewhere in the exam. So if you're just going to get sloppy on it, too bad. right? Or maybe not. They might just say, yeah, we don't.
How about you?
Me? I don't know. I might not care, but just remember they might. So you won't lose it here, then you'll lose it there. You'll never know, right? You'll just know I didn't get perfect on it. So you know what? I would consider making sure you do it. I probably won't take marks off. If it was just these specific values for the range, then we could list just specific values. If it could be anywhere in between those, then, okay, and we'll be more specific on a test. Set of all y such that 2.03 is less than or equal to y, is less than or equal to 68.11, and y belongs to the reals. Okay, so let's say that was like a soccer ball being kicked. Your domain range would look more like the bottom, right? It would probably be like, you know, this is time, the time we go from like 0 to 5. That's when it hit the ground. If this was height, it would go from 0 to whatever, 20 meters, let's say. It would be this type of domain and range, right? It all depends on the context, for which we have no context here, right? So we're saying, well, maybe it's this, maybe it's this, maybe it's this. Right? Like these are all the possibilities. And again, on a test, it will be clear which one you're supposed to do.
Should we be writing those down?
And if you want,
The actual one?
I would, but they're going to be in, they'll be in Schoology, right? All the notes will be put in Schoology. You might want to write them down with just sort of an explanation of, if we're just talking an exponential function, then it's these guys, right? That's just the characteristic of an exponential. If it's just a specific set of data, specific set, I can't say it. A specific set of data, if it's a specific set of data, only these, then this is how you would list the domain and range. This would be for a general exponential function, exponential. And if we knew that we could vary within this set, that would be this last example here. So any values within the set. Values within the set. So that type of thing, you've seen in 20-1, right? That would be kicking the soccer ball. We're talking about a quadratic. We know that it goes from 0 to 5 seconds. That's when it's kicked. 5 seconds, that's when it hits the ground. There's no point in going beyond that. You would never extrapolate beyond those because it's not going to drill into the ground. Right? It's not going to go below ground. And then for your heights, it would be from 0 ground level up to whatever the maximum height was. Okay, you'd be looking for that. This guy here. All right, so give this one. Is this growth or decay? Decay. All right, let's do it. So we're going to clear. And you go into the calculator. One of these days, figure out y. I can't see the calculator with that. I'm going to go to y equals. I'm going to clear out what's in there. I'm going to go second plus 4, clear all lists. Hit enter so it clears the lists. I'm going to go stat, edit, get back into the list. It's an L2. I'm going to make sure I move over to L1. And I'm going to put in my x values. 2, 4, 6, 8, 10, 12. So the other one was odd. This is even. And then I'm going to put in the corresponding y values, 102.8. Sounds like a FM station. 44.5. 17.2. So on a test, make sure that you go back over your numbers, make sure that they match up correctly, make sure that they are all correct. Because if you run a regression, it doesn't matter what kind of regression, whatever regression you're running, if you're off by 1 digit somewhere, you're supposed to put 22 and instead you've got a 2, then it's just wrong, right? Like the whole thing. And if it's numeric response, you're not even going to know, right? If it's multiple choice, you'll have oh, yeah, I didn't get any one of those answers. You go back and look at the table. So go back and look at the table before you move off of it, right? Just make sure all your numbers are correct. We do a scatter plot. This goes, we got to go up to 12. So maybe I could say, let's go to 15. This has to go up above 100 for the window. So let's go 0. Let's go to 15. By ones is fine, right? 15 kicks is fine. 0, let's go to 110. Take us up, and by 10 is fine. The stat plot should still be on, so if I hit graph, I should see the stat plot. Okay, and again, if you see error invalid dim, it means you cleared your list, but you're telling the calculator to do the stat plot, and it's saying I can't do that. There's nothing in there. Well, now we run the regression. So stat over to calc. So we know it's a 0. We could just hit 0. That'll take you right to exponential regression. If not, if it's off the screen, the easiest way is to just up arrow. That'll take you to the bottom of the list, and then you'll get there a little bit faster. If you feel the need for speed, right? Or you can just. I heard when you guys are clearing your calculator, and it's like 1, 2, 3, 4, 5, 6, 7. So like just hit 7. We'll go right to reset. Store regression equation. Okay, bars over to y bars. Enter twice. It'll put y1, so it's going to put the regression equation that it's about to work out when we hit calculate. And we got 250.96 and 0.64. So y is equal to 250.96 bracket 0.64 to the x. So if I was just looking at this, I would say, hey, that's exponential decay, because it's less than 1. What's the y-intercept?
250.96.
Right. So the y-intercept is the value of a. It's 250.96. What is the end behavior? So if we want to look, just hit graph. Right. Now we're actually only in Q1, but remember that's still going up and it's going to cross into Q2. So it is Q2 to Q1 and it's decreasing. Q2 to Q1, decreasing. Let's do the domain and range as if you can have any value between here and here. So for the domain, we'll just say set of all x such that 2 is less than or equal to x less than or equal to 12. So we'll do it as if we can actually draw that line. Okay? If you're doing the line, you're saying it's continuous, right? Not discrete data. Discrete data would just be the points. We're running the regression. We're going to say, okay, it's the line. And then the range would be from 1.3. So the set of all y, 1.3 is less than or equal to y. Is less than or equal to 102.8. Y belongs to the real. Any questions on that one? Or anything to do with exponential regression, right? So this is our what? We did linear, quadratic, cubic. That's it, an exponential. This is our fourth regression. Okay, so fourth type of regression. Some of us, it's our first regression, but the other three you need to know. 4 years ago, oops, question from the textbook. Those of you that have done the reviews out of the textbook may have noticed some of those questions on the test. It happens. They're there. Yeah.
I know right up to square root of I thought that the domain was just all the reals. Why is it?
So we're doing this table as if it's got to be within these values.
Okay.
Okay.
But
So I just,
technically,
if it's an exponential function, it's all real numbers.
okay.
If there's context to it, see, there's not enough context here, right? It's just like there's a growth, there's a decay.
Right.
So then it's one of three things, like we did with the other one, right? We say it's all reals, or it's just these specific values, or it's anything within this range. So for this one, we're just saying it's anything within this range. It will be very clear on the test which one you're supposed to do. 4 years ago, the Billans retired and decided to move into an apartment. Their annual rent for the 4 years is given below. So in the first year, so years since retirement, 0 means that's the first year that they have retired, right? But we're doing it as years since retirement, so it starts at 0. The rent was $9,600 that year. The next year it went up to $9,960. The next year it went to $10,344, and the next year went up to $10,752. As living expenses are wont to do, they generally don't drop, right? They increase. Can we model this by an exponential function? Best answer is maybe. Well, okay, then here's the question. Is it linear? So linear says to go from here to here, we're going up like $3,960, say $4,000. We're going up by 4,000 here, and maybe, but here, $360. We're going up by $360? No, we're going up by, so we're not going up the same amount each year. So if we're going up, and it's going up by an ever increasing amount, then it's likely an exponential. Okay. So yes, the rent is increasing, but not at a constant rate. Not at a. So if it's linear, it would be a constant rate, not at a constant rate. Generally speaking, anything to do with money is usually an exponential regression. Okay, and we'll look a lot because tomorrow's all about money. Without using the exponential regression, approximately what is the annual rate of increase in rent? Well, we can work that out by saying, well, what's the increase here? So we say, well, you started at $9,960. Or sorry, you started at $9,600. You went up to $9,960, which is $360 increase. We want what is 360 as a percent of 9,600. So then we go 360 out of 9,600, and then to turn it into a percent, we multiply it by 100. Okay. So just like you would do on a test, let's say you wouldn't want to get 360 out of 9,600. Let's say you got like 36 out of 50, right? You'd work that, and then to get a percent, you just multiply by 100. Okay, we got a number? 3.75. They say, well, it's increasing by about 3.7. At least the first time it increased by 3.75%. All right, let's find out if that holds true. Calculate the exponential regression function, round values to the nearest 100. Is the b value close or the same as what you calculated above? Well, I don't know. Find out. So we go back here, turn this on, go to y equals, clear that out. Anything else that was in y equals, clear it. Second, memory, go into the memory. Number 4, clear all lists. Hit enter. Go stat, edit. Okay, so here's our 4th try in exponential regression. So I hope you're doing each of these, right? More of these you do, then just the easier on a test when it comes time to do regression. So we've got year 0, year 1, year 2, year 3. Arrow over, $9,600 the first year, $9,960 the second year, $10,344 the third year, and $10,752 will be their 4th year there, right? It's years since they retired, so it's like 3 years since, but then the first year they retired. So they've been living there 4 years. We go stat, over to calc, you can up arrow and say, oh, there it is, exponential regression. Or once you see that it's a 0, you can just hit the 0, right? Generally, I don't do that. I should do that. But I don't usually. You know, hey, you got 6 hours on the diploma, and I generally give you extra time on tests, so very rarely are you at kind of a rush for time, but go vars, over to y bars, hit enter twice, right? Or whatever your calculator. So by now, you need to know how to run a regression in your calculator. Hit enter takes us to calculate. Hit enter, we get the equation. So 9595.43 and 1.03. I'm going to go a little bit further out on this. I'll tell you why, but not right now. I'll tell you why in a minute. I'm going to go 9595.43 and 1.0385. 1.0385. And then I have, of course, forgotten the first number, which was 9595.43. 9595.43. Is he saying round values to the nearest hundred? And we kind of are. Okay, we kind of are, but it's not sort of obvious. Is this b value close to the value we calculated above? Well, we didn't really calculate a b value, right? We calculated the increase. We said it went up by 3.75%. But we're looking at 1.0385. So what does that really mean? Let's find out. So 1.0385 tells us we're looking at exponential growth or decay. Growth, right? If it's over 1, it's growing. So now the question is, it's over 1, how much is it growing by? Well, here's how we do that. So what we do, we take the 1.0385 and we subtract 1. And we get 0.0385. Okay, so it's growing at a rate. So the 1 that's in front, the 1 just keeps the amount, right? That keeps that $9,600. And the 0.0385 is actually the growth. That's what it's growing by. So the 1 keeps the amount. 0.0385, that's the growth. Okay, so how do we make sense of that? I've got 0.0385. That's a decimal. To turn it into a percent, we're going to multiply by 100. Right? You want to turn a decimal into a percent, you got 0.75. You want to turn that into a percent, you multiply by 100, you get 75%. So here, we subtracted 1, multiply, and we get 3.85%, which we can now compare to the 3.75% and say, they're pretty close. Okay. They're pretty close. This b value, to get b, we really would have just done this. 9960 divided by 9600, right? Say, well, what are you dividing by? Or what do you, 9960 divided by 9600, right? And we get 1.0375. 1.0375. So that gives us the actual b value, right? So the b value, say, what am I multiplying this number by to get this next number? Well, the way we do it is we just reverse that and divide. Okay, we worked out a little more sophisticated. We worked out and said, well, what's the percentage increase, right? We said, oh, it's 3.75% increase, right? That 3.75% increase corresponds to a b value of 1.0375. So to take this and make it into a b value, the first thing you would do, so we take the 3.75, divide it by 100 to turn it into a decimal, and then we would add 1 to get the b value. So all the 1 is doing in the b value is keeping the original amount, and then whatever's left over, whatever's after the 1, that's your rate of growth. If your b value is 3.7, let's say, and you subtract 1, you got 2.7, and then you convert that to a percent, it'd be 270. You're growing by 270%, right? So you're growing, that would be your growth rate. So if your b value is greater than 1, that says exponential growth, then here's what you do. Subtract 1 from it, get the decimal, multiply that by 100, that's your rate of growth. Okay, now let's go back up and look at this guy, which is decaying. What does 0.97 mean? So we have 0.97, which says decay, right? Decay. So what is the rate of decay? How much is it going down by? You're going down by 0.97? Yeah, 0.03. So here's what we do. If the b value is less than 1, then we go 1 minus this number. Okay, so if the b value is greater than 1, you subtract 1 from it, and then you turn it into a percent by multiplying by 100. If the b value is less than 1, you subtract it, the b value, from 1, which gives you 0.03, and then you convert that to a percent, right, and that gives us 3%. So it's going down by 3%. Okay, we'll cover this more tomorrow as well. We'll go into this again tomorrow. But if your b value is less than 1, so think about it. What's happening here? The 0.97 is you're saying, I'm going to retain 97% of the value. So if I started with $100 multiplied by 0.97, I would have $97, right? How much would I be down? $3. 3 out of 100 is 3%. It go down 3%. Okay? So for the rate of decay, you're going to do this. 1 minus the b value multiplied by 100, and this says the rate of decay is 3%. The b value that goes with that is 0.97. Right? And what that b value is doing is just, again, it's retaining value, right? It's retaining 97% of the value of whatever it is that you put in. If your decay rate was 97%, right? This isn't going down by 97% each time, right? If you put 0.03 there, then it will be dropping by 97%. You'd only be retaining 3% of the value each time. So what's gonna be messy notes, random lines. What's the growth rate in percent here? What percent growth is this doing? 54%, right? So 1.54 minus 1 is 0.54. 0.54 times 100 is 54%. This is growing at 54%, right? So about half again each time. 0.64, what does that mean? How much is it going down by each time? 36%. I heard it was muffled. It's like you're speaking through a piece of cloth or something. Yeah, and yawning at the same time. So, okay, we got the yawn and the mask. So 36%, right? So less than 1, it's decay. So what do? We go 1 minus a number that's less than 1, multiplied by 100, turn it into percent. If it's greater than 1, we subtract 1 from it, multiply by 100, and get the rate of growth. So here, 1.0385 works out to a growth rate of 3.85%. What will they pay in 10 years? Okay, let's go into here, turn that on. So let's set a window. So 0 to 15 will work, right? That'll take us to 15 years. But it's like $10,000 range. So here's the thing about Y values. I always really like to start at 0, right? Even though technically we should be starting around like 9,500 or something. But I just kind of like to see it, hey, if that's 0, you know, oh, we're way up there. But so how far up do we have to go? We know we're at 10,000. Let's go to 15,000. Okay, and we'll go by thousands. So your scale really doesn't matter. It doesn't matter what scale you put in. If you did a scale of 1, it would just try and draw 15,000 ticks, which it couldn't do. And you just end up with an axis that's kind of fuzzy. You don't actually see any ticks on it. which is not a big deal. Okay, hit graph. So our stat plot is still on. We're going to see the 4 data points we have. There's our line, right? So we can see that it's growing. It's growing at like 4% a year, 3.85% a year. So in 10 years, okay, second calc, we want to value x is equal to 10, and we get $14,000 and 64 cents. We'll just go with 14,000, right? Oh, rounded, there you go. So $14,000. Wait, was it 63 cents? 14,001. $14,001. Now, if I'm rounding the nearest dollar, I probably shouldn't. Okay, so second calc value x equals 10. Any questions? Yep. Oh well. Like Connor. Did you put it into y1? When you ran the regression, did you go y1? Did you set your window? So if you're worried about it, it's something like, hey, my name graph, go second function graph, right? So if you go second function graph, it's going to take you into the table. And you can see, okay, if I'm looking at 0 to 10, I need to go from like $9,500 to $14,000. Like it'll give you an idea as to what your window should be. Then go check your window. Sometimes we leave a 0 off in the window, right? And then you're not actually looking, you know, there's no data in where you're looking.
With that, why wouldn't you just go look at it in number 10 and then get your 14,000
You can do that. So you can look in the table. If it said 9.5 years, not in the table. But yeah, certainly looking at the table is perfectly valid, right? But I like to see pictures. It's a pretty picture. Right? It's growing. We will see what exponential growth. We are living exponential growth right now, but we will see what exponential growth does, especially with money, and that's going to be in tomorrow's lesson. And